Recording in progress.
Hi students, in the last lecture we have discussed up to Ohm's law. Let us see now statement of Ohm's law and important points on that. So we have derived that I proportional to V. Then statement is at a given temperature, current in a conductor is proportional to the potential difference across its ends. So this is macroscopic level, means we are seeing as a whole. Now same thing. So we got relation J bar equal to sigma into E bar, and sigma is a constant at a given temperature. So we can say J bar proportional to E bar if if temperature is constant. So statement is now at a given temperature, current density in a conductor at a point, this is at a point, is proportional to the strength of the field. This is now microscopic level. So this is from point to point inside conductor. This is in a conductor as a whole. That's why macroscopic and this is microscopic. Okay. Right. Next. A material that obeys Ohm's law is called an ohmic conductor or a linear conductor. And for ohmic bodies, IV graph means current versus potential difference. It is a straight line. And a material that does not obey Ohm's law is called non-ohmic or non-linear. And here most important point, that is R equal to V by. This is giving us resistance of any body. It need not be ohmic or non-ohmic. It can be any body. Generally, measured having a misconcept like it is only for Ohm's law. That means only for ohmic bodies. That is a wrong concept. This is giving us resistance of any body. It may fall obey Ohm's law or maybe not obeying Ohm's law. Okay. Let us see once regarding graph. We can expect simple problems. So taking a graph, suppose we are taking current on vertical axis and potential difference on horizontal axis. Suppose graph is given like this, passing through origin. It is a straight line making angle theta with the horizontal axis. You can see here slope. Slope is now tan theta. Slope is tan theta, which is equal to I by, right? So we are knowing that V equal to I into R. And see here what we got slope. Slope is I by V. Means in this slope is giving us a reciprocal of resistance, right? I by V gives reciprocal of resistance. Suppose question is given like at a given temperature, at a given temperature, given two graphs like one makes angle theta 1, other makes angle theta 2. So for two ohmic bodies, means which are obeying Ohm's law, given current versus potential graph. Let us say this is now resistance R1 and this has resistance R2. Now question is relation between R1 and R2. Okay. So here we have seen that slope is giving us reciprocal of resistance. This is reciprocal of resistance. So more angle means more slope. Slope is more means R value is less. That means in this R2 is less than R1, right? See once slope is more means 1 by R value is more. That means R value is less. That's why R2 is less than R. Suppose graph is given like, if graph is given, this is a potential difference across a conductor, means across the ends of conductor, and this is a current in the conductor. Now in this case, slope gives us, if this is angle theta, so the slope is now tan theta, which is equal to V by I. That means in this slope is giving us resistance. That means if you're having same graph but taking here potential difference and here current, then answer will be more slope means more resistance. That means then we are going to get here R2 greater than R1. Okay. So graphs for ohmic bodies, they are straight line. If they are not satisfying Ohm's law, then graph is not a straight line. Okay. Right. So these are the points regarding Ohm's law. And here we can focus one more thing regarding the problems based on R equal to rho L by A. Let us see once. Let us take, we got R equal to rho L by A, this relation. They're asking some simple questions like a conducting wire is stretched. Its length is L initially, length is L. Now it is stretched to, it is stretched so that length becomes now n times the initial value. So if initial resistance is R, what is the final value? Okay. We're asking question like initial length L, cross section area is C. While we are stretching, cross section area changes. Okay. Then how resistance changes? Let us see now. R equal to rho L by A, multiply and divide with L. So it becomes L square. This is now A into L. Rho is a constant. A into L, it is a volume. Volume also constant. Therefore, it is now rho L square by V. Since volume constant, rho constant, L proportional to, sorry, R proportional to L square. That implies R proportional to L square. That means if length becomes n times, resistance becomes n square times. Resistance becomes n square times. Okay. Now same thing in terms of cross section area. See what we can do. R equal to rho L by A, multiply and divide with the cross section area. It becomes A square. Now L into A, this is a volume, which is a constant. Rho is also a constant. Remaining is now A square. So this implies resistance is a proportional to 1 by A square. And we are knowing that A equal to pi R square, means if it is a cylindrical wire where thickness is very small, cylindrical wire. Then this is a proportional to 1 by R power 4. So we can expect problems like if R becomes a half on stretching the wire, how resistance changes. Or if length is doubled, how resistance changes. Or we can write the same expression in terms of density and mass of the wire. See once. See here what we got. R equal to rho L square by V. Now multiply and divide with density. Then see what we get. Volume into density, that is mass. Okay. Rho L square density by mass. Now they can ask questions connecting mass, length, density. Okay. This is one relation. Now let us take from here. So from here, what we can write? R equal to rho L A by A square. Now again multiply and divide the density. L into A, volume. Volume into density, mass. This is mass. So rho M by A square D. This is in terms of mass, cross-section area and density. This is in terms of mass, density and length. So we can expect any kind of the combinations like asking problems based on the results, right? Let us see problems. You can see the first two questions just now we have discussed. A resistance of a conducting wire is R if it is stretched so that its length becomes n times its initial length, then find its resistance. So it becomes n squared times, right? Right. Next, a resistance of a conducting wire is R if it is stretched so that its radius of cross section becomes 1 by n times. So radius becomes 1 by n times. And we have seen that resistance proportional to 1 by R power 4. Okay. That means it becomes now n power 4 times. Resistance becomes now n power 4 times. So like this directly we can solve these problems. See next one. The current density at a point is given as J bar equal to 2 10 power 5 into I cap cos 37 plus J cap sin 37 ampere meter square. Find the rate of flow of net charge through the cross section area S bar equal to 3 I cap plus 4 J cap centimeter square. So you can see this is centimeter square, means 10 power minus 4 meter square. Means this is now very small. So just like a point, right? And we are given here J bar at a point. Now we have to focus through this area. What is rate of flow of net charge, which is nothing but current, right? Now see calculation of that. So first write down given data. J bar equal to 2 10 power 5 I cap cos 37 J cap sin 37 ampere per meter square, right? So we have to find a current and S bar is given 3I cap plus 4J cap centimeter square, right? So we can see here, this is a simply a point, right? Because area is very small. Directly we can write I equal to, actually definition of J bar equal to di by ds. Okay. So here what I can write directly, I equal to J bar dot S bar. Okay. Because throughout this area, J bar is the same, right? Now see calculation part. See here what we can do. Cos 37, 4 by 5. Sin 37, 3 by 5. I'm taking 5 outside. This is now 2 by 5, 10 power 5. It is cos 37, 4 by 5. It is 4I cap, 4I cap plus 3J cap dot S bar. 3I cap plus 4J cap given centimeter square. So 10 power minus 4 meter square. Okay. Now you can see the value how much. This is 10 power minus 4. This is 10 power 5. You can cancel this one. Remaining is 2 tenths. Okay. Or 5 here. 2 times 2 2s are 4. This is a 4. Remaining is now 4I cap dot 3I cap. 3 fours 12. Next 3J cap dot 4J cap. 3 fours again 12. 12 plus 12, 24. 24 fours. It is 96. So 96 ampere. This is now the current passing through that area. Okay. It is a very simple question. Let us see the next one. See the question given. A metal block has length, breadth, and thickness. Values given. Find the ratio of maximum to minimum resistances of the block. Right. Let us see how we are solving this maximum and minimum. Length, breadth, and thickness 50, 20, 30. So write down the given data. L value 50 centimeter, breadth is 30, and thickness is 20. And we have relation R equal to rho L by A. Now see, R value is maximum. See the possibilities now. To get R maximum, rho is a constant, remaining L. You can see among these values, this is now maximum value 50. So if L is maximum and A value minimum, now cross check for these three, for which combinations A value minimum. If I am taking for these two, area 150, and for this combination area is now 60. And if you take now this combination, area is now 100. So area is least if you consider this combination 60. So I'm taking length is now 50 because that is maximum by area is now 30 into 20. Okay. So 30 into 20. That is R maximum. Now we can see R minimum. So it is a minimum when L is minimum and A value maximum. So you can take if current is a passing along thickness. If current passes along thickness, okay, along thickness, then see area will be 30 into 15. It is 150. So it is the parallel to thickness current flow. So 20. This is a 50 into 30 maximum area. So now see ratio R maximum by R minimum. So rho gets cancelled anyhow and zeros also gets cancelled. Just focus the values 5 by 5 by 6. This is now 2 by 15. Check it once. R maximum. I have left zeros here. It is now 5 by, or I can take it as a 5 by 1, 0, 60, 5 by 60. 5 by 60, 1, 0. This is now 1, 0 gets cancelled. 2 by 2 by 350 is 150. 2 by 150. Okay. 0, 0 gets cancelled. Remaining is now, see what we can do. 3 table, 3 here 2 times, and 3 here, 3 here, 5 times it, 5 3 is 15. So 25 by 4, that is now ratio. Okay. So when we want to calculate maximum, we have to maximize L and we have to minimize A value. Okay. And to get minimum, minimize L value and maximize cross-section area. Right? See, next problem. A hollow cylinder has length L. Inner radius and outer radius are A and B. It is made of a material of resistivity rho. Find the resistance of the cylinder if current flows radially outwards, current flows along its length. Okay. Now see what we can do. So we are knowing that resistance depends on which direction current is flowing. So first one given, current flowing radially outwards. So we are seeing this from the top. It looks like concentric circles when we see from the top. Okay. Inner one is A radius and outer one is B. So now imagine a coaxial cylinder of radius R. Imagine a coaxial cylinder of radius R. Its thickness equal to dr. Thickness is dr. This thickness is dr. So when current flows radially outwards, that thickness becomes length. I am repeating. When current flows radially outwards, that thickness becomes radius. Sorry, that thickness becomes length. So resistance of that coaxial cylinder, it is given by its resistance is given by rho L. L is now dr area. It is flowing radially outwards. Area means we have to focus now the curved part area, which is equal to curved part area equal to 2 pi r L. Okay. And you can see here When current flows radially outwards, it has to pass through each and every shell from R equal to A to R equal to B. So through all these same current flows, and while passing, resistance will add up. Resistance of this shell, and next resistance of the next one, it will add up because current flows radially outwards. So we have to add up all those resistances. So we have to integrate. That means we are finding resistance of one coaxial cylinder. Like this, we have to find resistance for all coaxial cylinders. Then we have to take sum of all these things because through each and every coaxial cylinder, same current is passing. Okay. Now integrate from R equal to A to R equal to B. Then see what we get. Rho upon 2 pi L constant, take outside. Remaining is 1 by R dr, that is ln R. Ln R and take limits now. It becomes ln B by A. Right? This is our final answer. Rho upon 2 pi L into ln B by A. Now in this second one is, the second one is, if current flows lengthwise, if current flows lengthwise, if current flows lengthwise, simply see what we can do. Resistance R equal to rho, L is L only. Coming to area, it is outer area minus inner area. So B square minus A square. So it is a very simple and direct one. Okay. So like this, we can solve questions based on calculation of resistance. Okay.